Now, with mathematical induction, of course, it's quite a powerful technique, but there are certain things we have to be careful about when applying induction. And this is an example, a very classical example we can encounter in texts dealing with this subject. And let's first of all read this proof, which is a false proof, let's say, and try to figure out what went wrong. The proposition that we would like to prove, so to speak, is this. The proposition that all horses in a set of n horses for any n positive integer are the same color. Okay, so this is the proposition, and it is ridiculous. We obviously know this is false. But here is a proof using induction, and we would like to figure out what is wrong with it. Basis step, n equals 1. So that's a set of horses consisting of just a single horse. And clearly P1 is true for this case because there is just one horse. So every horse in the set has the same color. That is trivially true. Now in the inductive step, assume that Pk is true, and if we can show that Pk plus 1 is also true from this assumption, we will conclude that P of n is true. Now, what does P of k being true entail? All the horses in any set of k horses are the same color. So you have horse number 1, horse number 2, horse number 3, let's say, up to horse number k. Based on our assumption, they have the same color. Consider any k plus 1 horses, okay? Now, of course, label them from 1 to k plus 1. I'll have k plus 1 here, let's say. Now, look at the first k. Due to my assumption, they are all of the same color. But then look at the last k, from 2 to k plus 1. Okay? Again, this here is a collection of k horses from 2 up to k plus 1, right? And based on the assumption, they also have the same color, right? And since we have an overlap here, right, that means h1 and hk plus 1 here should also be of the same color, which means all of these k plus 1 horses should be of the same color. And combined with the basis step, by induction, we see that P of k or P of n is true for all n. Okay, so this sounds correct. What went wrong here? The problem in this proof, well, it's not a proof, obviously, it's wrong. The problem with this argument is apparent when n is chosen as 2. Now, let me clear all this. Okay, the problem was with the overlap, because if you just have 2 horses, you have horse 1 and horse 2. This is a collection of a single horse, and due to the basis step, it's of the same color with itself, obviously. And this is another one, a collection of one horse, and this is a collection of, well, in the case of k equals 1, this is a collection of k horses, and this is a collection of k horses, but you see they do not overlap, right? So we cannot actually conclude that both of them will have the same color. So what is the problem here? The problem here was the selection of the basis. The basis step should have been n equals 2, right? Because only then, if you just have, if you have 2 horses, h1, h2, and h3 is added, only then, when you just look at the first 2 and the last 2, there will be an overlap. For this to be true, your basis step should have been 2, in which case the basis step would have failed, obviously. So this would not be a valid proof. This demonstrates choice of the basis is extremely important. The basis step and the inductive step are not really entirely separate Okay, you have to consider the relationship when you assume a value for the basis, what that entails in terms of the inductive step. Therefore, the choice of basis is of utmost importance. Okay, another very important concept we are going to talk about is called strong induction. And this is sort of an alternative formulation of induction. Its statement is different, but we will see that it's equivalent. So the statement here is P1 and P2 and P3 and up to Pk, whatever k is. Essentially, this is a collection of k basis steps, let's say. And then for all k, P of k implies P of k plus 1, so the inductive step is the same, okay? Then this implies P of n is true, okay? So the difference between the statement we have seen earlier for mathematical induction and this particular statement is these. So what happened here? In our basis step, we start again with P1, but in our inductive step, our assumption is not just the truth of P of k, but we also assume P of n is true for all values from 1 up to k, not just P of k. Okay? So this is what we call strong induction. And the inductive step assumes P of n true not only for k, but for all values from 1 up to n. Sorry, up to k. So this should be n less than or equal to k. Okay? Now, the name is strong induction, but strong induction as an argumentative tool is not stronger than mathematical induction. Okay? Actually, they are equivalent. They are equivalent in the sense that a proposition that can be proved using one can be proven using the other. Okay? So in that sense, they are equivalent. We call this strong induction because essentially doing proofs with strong induction is usually easier. Okay? And the reason that they are equivalent is because they are implied by the same principle, the same axiom, let's say. They can both be derived from what we call the well-ordering property. Okay? So let's look at what this is. The well-ordering property states that every non-empty set of non-negative integers has a least element. Okay? Now we can show that a mathematical induction follows from this, and let's see how this is possible. Assume P1 and Pk implies Pk is plus 1. Now these, well, you see this is the basis step and this is the inductive step, obviously. And what we are going to do here is we are going to do a proof by contradiction. Okay, so we are going to assume these hold, but P of n doesn't hold for all k, for all n. Okay, for that we are going to assume P of s is false for some s. So there is some s value that P of n fails. Okay, and then we'll define a set S as the set of integers for which P of n doesn't hold. So clearly S is an element of this set. That means set S is not empty. Okay, now S is a set consisting of integers. It's not empty, as we have established. Okay, so it's a non-empty set of non-negative integers. Therefore, by the well-ordered property, it must have a least element. Let's say that is M. That minimum element or that least element is M. Now, if M equals 1, that's a contradiction because we have assumed P1 is true. Okay, therefore 1 cannot be in the set S. That's a contradiction. So let's look at the case where M is greater than 1. If M is greater than 1, then M minus 1 is greater than or equal to 1, and P of M minus 1 must be true, right? Because M minus 1 is not in the set S. Why is that? Because M itself is the least element in set S. So M minus 1 cannot be in the set S because it's less than n. Okay, that means P of n minus 1 must be true. But based on this assumption here, the truth of P of n minus 1 implies P of n, right? But this is a contradiction because m is in set S, which consists of the integers that make P of n false. So this leads to a contradiction. Therefore, there cannot be any elements in set S. Therefore, P of n should hold for all integers. Okay, all positive integers. So this is how mathematical induction entails from well-ordered property. And in fact, if you assume well-ordered property as an axiom, you can prove induction, and it's also vice versa. If you assume induction, you can prove well-ordered property, or if you assume well-ordered property, you can prove strong induction, etc. So these all imply each other. I'm not going to do the proofs, but essentially this shows us that mathematical induction and the statement what we call strong induction are equal. So they are as strong as each other in terms of being able to prove statements.